Hello everybody and welcome to our webinar. Today we will speak about using QuickField software for optimization. We will show you various options and explain how to apply them to different types of problems. And we hope to prove that optimization, as any other type of analysis with QuickField, may be really simple, straightforward, and generally fun. My name is Vladimir Padnos. I am Director of Marketing and Support here at Terra Analysis, and my short introduction will be about the features of QuickField, which make it convenient and efficient tool for engineering optimization. Let's begin. QuickField is a finite element analysis software with very wide range of analysis options. It may be applied to a variety of electromagnetic, heat transfer, and structural analysis problems. This slide shows what is available in QuickField 6.0. A family of magnetic packages includes DC magnetics, AC magnetics, and transient magnetics. Electric suite includes electrostatics, DC and AC conduction, and also transient electric analysis package. Thermostructural suite includes steady state and transient heat transfer and stress analysis. What is important that QuickField is multi-physical software, and it is possible to combine several types of physical setups on the same geometry, import results of one analysis in the another simulation, and perform the complete multi-physics model simulations. Generally, the same word may be said about many other finite element packages available today, but QuickField has additional features which make it extremely efficient tool for engineering optimization. First such feature is extreme speed of solution with QuickField. This is based on our special solver technology, which we call DDM, domain decomposition method. This gives QuickField quasi-linear dependency between the solution time and number of mesh nodes, or accuracy. Traditional finite element solvers have second order of this dependency, so if you increase number of mesh nodes twice, you expect that solution time goes up 4 times. But in QuickField, it increases only twice. This is not as important if you need to solve just one problem, because most of the time engineer spends on the geometry definition and result analysis. But for optimization, when you need to compare results of hundreds of problems, speed of solver is most important. Other important feature of QuickField is its expandability. In addition to simple and straightforward user interface, QuickField also features a full-blown application programming interface, which is organized as an open object library. This technology is called ActiveField, and it allows interaction between QuickField core and variety of other programs, from custom development software to MATLAB and Microsoft Office scripts. It also assures communication between the QuickField core and parametric analysis utility called LabelMover, which is directly related to today's topic. ActiveField API is part of all QuickField editions, including Free Student Edition, and explained in details with many examples on our website. This application interface allows automation of any repetitive tasks, and optimization is obviously one of such tasks. Let us discuss what types of engineering optimization may be automated with QuickField. Roughly, we may separate 2 classes of optimization projects. Major design optimization, which requires deep modification of design, changes in the physics, technology, and basic operation principles, of course, should be performed by experienced engineers, and there is not much of automation possible today. For such situation, QuickField may be used as a convenient tool for fast checks of possible designs. Main impact here is on the human creativity. But for minor design adjustments, computers may do much more. Of course, even with small design adjustments, changes may be too large and require full-blown human operator supervision. But there are many practical situations when the geometry should be modified, but within the same topology, or physical properties need to be adjusted, but the model will stay in the same physical setup. And here, automatic procedures may be very efficient. For these situations, which require small variation of the geometry of physical parameters of existent QuickField model, you may use the free parametric analysis utility tool called LabelMover. LabelMover operates in three modes. In serial analysis mode, you define a set of steps which modify specified geometrical or physical parameters of QuickField model objects, and define which of processor results are to be controlled. LabelMover will automatically generate a series of problems, solve them, and populate the table with results. Tolerance analysis allows study of the statistical distribution of specified result with known statistics of the geometrical and physical variation of the model objects. And optimization allows you to modify model parameters to achieve some goal value. Optimization in LabelMover works with built-in algorithms, which are usually fast and efficient. This slide shows our website page with many simple benchmarks proving this fact. But in case your model requires some special optimization algorithm, it is also possible, and you may use external programs which communicate with LabelMover through application programming interface. And then LabelMover controls QuickField via ActiveField. This makes QuickField very flexible and powerful tool for many practical optimizations. But most important, this vast range of features doesn't make QuickField complicated. It is still simple and requires no special training. Optimization with QuickField may be done with the same level of simplicity you are used to work with when you create finite element models. My colleague Sergey will now prove what QuickField is simple and powerful tool for optimization using practical examples and with presentations of finite element models.
Today, I'd like to tell you about solving optimization problems in QuickField. I want to start from describing the difference between simple or direct problems and inverse problems, which are typically solved as optimization problems. In direct problems, the task is to find solution based on the given set of data. For finite elements problems set up with QuickField, these parameters include geometry, material properties, and field sources, as you can see on this slide. In inverse problems, we need to find the combination of parameters which lead to a prescribed solution. Usually, the solution of inverse problem requires solving of many direct problems, and in QuickField, this may be automated using parametric utility LabelMover here, and LabelMover generates and controls a series of QuickField calculations. Those problems are very common in practical engineering. Design of the device may generally be considered as an inverse problem because at the beginning we typically have required specifications of future device and nothing else. And design of the device is a result of engineering work. For example, we want to create a kettle that will be able to boil 1 liter of water in 2 minutes. At first, we have only this goal. Then, during the design process, we identify the needed parameters, estimate their values, perform the reliability check, analyze the performance and reliability of the design, and so forth. This is the main type of the inverse problems: design, identification, diagnostics. Solving of the inverse problem using LabelMover could be split into 3 stages. First stage is setting of goal and values. Goal is the result value we want to achieve. It can be some physical value, heat flux, electric current density, stresses, and any integral or local value calculated directly in QuickField. Other results calculated in QuickField may be defined as values in LabelMover, which are just displayed optionally. Second stage is setting of the variation method and the limits. Parameter of optimization is the position of a geometrical object, like body, edge, or vertex, of a physical property, electric potential, Young modulus, thermal conductivity, and other media properties of field sources, depending on the problem type. I will show you how to set this information. And the first stage is to press the optimization button to get results. But in addition to solving optimization problems using LabelMover and built-in optimization algorithms, there is also an opportunity for using external programs which interact with QuickField or LabelMover using application programming interfaces. And you can create those interfaces manually. This may be required if built-in LabelMover optimization algorithms are not working well for your type of model, or you are developing the new optimization method and you need to test it, or any other reasons. And today I'd like to show you how to integrate QuickField, LabelMover, and Visual Basic for application scripts. And we choose a Monte-Carlo algorithm for this. Using LabelMover, we will assign the set of parameters to vary, and then the base script will invoke the set of variations, which LabelMover then performs using low-level interface to QuickField core. And our implementation of Monte-Carlo optimization uses random variations of the parameter within the specified range using this formula. And for each variation, we calculate the result in QuickField and compare them to find the minimum. You will see that only the best current results of optimization will be displayed. There are just a few lines of code needed to implement Monte-Carlo optimization. We highlighted 4 logical blocks in this script: declaration of values, reading of values from the spreadsheet, initialization of values, and the cycle itself. And in this cycle, random parameters are generated, and LabelMover runs QuickField and extracts the result for these variations. In fact, the essence of this code are free calls to LabelMover. Let's take a look at this code. There are just a few lines of code needed to implement Monte-Carlo optimization. We highlighted 4 logical blocks in this script: declaration of values, reading of values from a spreadsheet or data input, initialization values, and the cycle itself. In this cycle, random parameters are generated and LabelMover runs QuickField and extracts the result from it for these variations. In fact, the essence of this code are free calls to LabelMover. Let's take a look to the DBA script and explore how it looks like. So the method set variation, set parameters, get results. This is the get results method. Starts QuickField simulation for these parameter values, and also get results method returns the calculated result for further analysis. It's really simple to understand and modify if needed. This script will be published on our webinar webpage. You may try and maybe improve it yourself. And before we start, I'd like to do one practical comment. Before you start using Excel scripts with QuickField and LabelMover, you should link the corresponding object libraries, because LabelMover communicates with QuickField core using active field, whilst our application controls LabelMover using its object library. So we go to Tools, References, and link QuickField LabelMover and QuickField object libraries to our program. Now let's study some examples. First example is a heat transfer problem. Here we are going to vary radius of the external insulation layer to get the heat flux of 21 to 0 watts, as you can see. Slide. Now let's go to QuickField and try to solve this problem. So that's a geometric model, and the problem properties are the following. It's a steady state heat transfer problem. Mover class is сегодня That's a geometric model, and problem properties are the following. It's a steady-state heat transfer problem. Module class is playing parallel, so that we set length in z direction. Length units are millimeters, coordinate system Cartesian, and precision is normal. Okay. Now let's study this model in details. What do we have? We have a steel. It's a pipe made of steel. We set thermal conductivity here. It equals 42. Also, we have asbestos. Asbestos is insulation. We also set thermal conductivity of asbestos. And we have edge labels and lattice labels. To solve direct problem, we should set some boundary conditions. On the inside boundary, we set convection boundary condition with convection coefficient and the temperature of the ambient media. Means that the temperature of the steam equals to 150 degrees centigrade. Also, we set convection boundary condition on the external surface. It's convection coefficient and the temperature of the ambient media, that is the air. The temperature 20 degrees centigrade. Okay. Also, we set some edge and lattice labels to solve this problem. We choose this boundary. We call this arc X. We set no properties for this boundary, and this edge will be needed to do optimization, because we will calculate heat flux passing through this surface. And also we have this lattice. We will control the radius of this lattice. I mean the distance from the 0 point to this point, because we'll change radius of this external boundary. Okay, let's go to LabelMover and do this optimization from scratch. Okay, let's start. First, we should add values in goal. Our goal is to reach the prescribed value of the heat flux passing through this arc-X edge or boundary. So, goal settings. Goal is close to minus 2120. This sign minus means that the direction of the heat flux is the direction towards the external direction. Okay, and also we want to add down that value. And this value is a radius coordinate of the vertex on the external boundary. So we choose quantity radius, and we don't use it as a goal. We just add this value. Now let's add the ratios. We're going to scale outside boundary with a factor of 0.5 to 2. We add it. And now we're ready to do optimization. Let's do this. That's how the built-in optimization algorithms of LabelMover works. You can see that LabelMover is reaching to the optimal solution. That is, on the 7th step, LabelMover did its best. That's an optimal solution. It's a little bit different from the first stripe, but it's pretty good. Now let's try to solve this problem using our Monte-Carlo algorithm. That's our Microsoft Excel spreadsheet, and here we're going to set some parameter to do optimization. So we should set lower and upper limits of variation. Lower limit means a limit for scaling. It's 0.5, and upper limit is 2. Let's set number of duration for 10, and the goal for 2120. Now we're ready to do optimization. Look here. Now we're ready to do optimization. That's our Microsoft Excel spreadsheet, and we're going to set some parameters in order to do optimization. This lower and upper limits are actually limits for scaling. It was 0.5 and 2. Let's set number of iterations for 10 and the goal for -21 to 0. Now we can open our Monte-Carlo script and run it. Look to this table. So that's the first result. The function value and parameter value. You can see that the second one is slightly better. Meanwhile, LabelMover is doing the same job as in the previous case. It's just solving the problem step, but the point is that QuickField, at first LabelMover, is driven by the external algorithm. So the optimization is ended, and that's the best result that we could achieve. It's not as accurate as those that we obtained in LabelMover, but we are not concerned about the accuracy. Now let's study another example, a magnetic problem. You can see the device. It's a gear with a winding, core, and a plunger. When you turn on the current, this plunger will. Now let's study another example. It's a magnetic problem, calculation of required core cross-section of a drive. The principle of operation is that simple. When you turn on voltage on the winding, the plunger begins to move because counter-motive force acts on this plunger, trying to pull it to the inside. So we have a goal, we have an exact solution, and let's try to solve this problem in LabelMover and then using our Monte-Carlo script. So that's a problem geometry model. This is problem properties. It's a problem of magnetostatics. The model class is axisymmetric. Also, we set type of units, coordinate system, and precision. So we have blocks. At first, we have plunger. That's plunger. We have the core. We have the winding. Insulation. Insulation is very thin. And the air, which surrounds the device. We set constant magnetic permeability for plunger and for the coil equal to 1000, and winding, insulation, and the air are the same in terms of magnetic properties. The source of the magnetic field is the winding. That's current density. And also we set boundary condition on the outside boundary. This is a property of zero magnetic potential. And also we set one edge. We create one edge for the LabelMover analysis. We're going to move these two edges selected as one. Okay, now let's do optimization. First stage is to add values. Not values, but the goal. First, I select plunger and choose a quantity of mechanical force, and I want this force to be close to minus 13 to 0. And I add this goal. And it's okay. The second step is to add variations. I choose this edge label called curve 1, and I'm going to displace this edge in vertical direction. So I set limits for horizontal direction for 0 and 0, means that no displacement will be carried out in this direction. And for vertical direction, I set .039 meters or 39 millimeters. So this is limits for vertical displacement. And I add this variation, and now I can do optimization. In the background, you can see what is happening. LabelMover moves code 1, which is the edge label chosen for optimization. And it seems that the optimal solution will be obtained very soon. Okay, the best result was obtained on the 6th iteration, and it's pretty good. Okay, now let's solve this problem in with our Monte-Carlo script. We open our Excel document and change lower and upper limit for variation. It's 0 and 0.039. It means that variation for the vertical displacement will be within these limits. We will not change number of iteration. The goal is minus 103 1,300 newtons. So we opened our Excel document, and now let's change lower and upper limits and the goal, because number of iteration will be the same. So let's do it. As you can see, the routine is quite the same as in LabelMover. Let's open and run our code. The result will be displayed here. And now let's open and run our LabelMover code. VBA code. The results will be displayed here. That's what is happening in QuickField. And now the step number 7 is carrying out. Let's wait a little bit. Well, our code did a pretty good job because the error is not so big. Let's calculate it. Well, our code did a pretty good job. Let's calculate the error. It's an absolute error. Well, it seems that our code did a pretty good job. And let's calculate the error. Well, it seems that our code did a pretty good job. This result is really good. And the first problem is a mechanical problem. In this problem, we're going to calculate allowable force for this Dynamo wrench. You can see the task on your screen and the exact solution. Now let's solve this problem in QuickField. That's our geometric model. It's a simple Dynamo branch. That's a problem properties. It's a stress analysis problem. Model class is a plane parallel. And also we set length, units, coordinate system, and precision. And by the way, since it's a stress analysis problem, we also set a formulation of the plane stress. Okay, here we have a steel wrench. We set Young's modulus, so Poisson ratios. Okay, and also we set fixation boundary conditions here. Means that prescribed displacement is 0 in both directions. Also, we have two lattice labels. We apply the force in this point, this external force acting in the horizontal direction to the left, because we set minus sign before the value. And also we have yet another vectors called control point. We will control value of displacement in this point. And now let's do optimization. First, let's add values and goal. Our goal is not to reach a prescribed value of displacement given in millimeters. We add it. And also we should add variations for the force. Now it's a variation of properties. We select force, then external force for x, and variation from 20,000 to 5,000. We add these variations and do optimization. This is the case then that the first step, or a zero step, was even better than the first, but as you can see, after that LabelMover decided to reduce the value of the force, and on the first iteration the optimal solution was obtained. And now let's solve this problem using Monte-Carlo algorithm. First, let's clear this content. Now, we just set a lower and upper limits for variations. And the goal. We open our VBA script and do optimization. and even from the fourth iteration, you can see that our algorithm reached a pretty good result. So that's a best result obtained using Monte-Carlo optimization.